So without further ado, let's do a quick few minutes on CAD for manufacturability, which is going to require us to actually talk about what we mean by manufacturability and how we actually make things. So manufacturability, or design for manufacturability, is designing something so it's actually easy to make. That you can model almost anything, but making things is slightly different. You can absolutely model things you can't make. So let's talk about the different manufacturing systems. Now, these are very kind of broad category overviews, and everything I'm mentioning here is something we have at the Bechtel Center. So first on the list, and should be first in your mental toolbox of how to make something, is sheet processing. Sheets of material are cheap, and they are available in almost any kind of size, any kind of quantity. They're commonly available, they're available fast. Secondly, sheet processing machinery, and what we have going on in the video here is a water jet, by the way. It's actually firing a blast of water with abrasive sand loaded into it through a tungsten sheet. You can see the processing is really fast on thin sheets. I mean, it just can literally make large complex designs extremely easily. And another example would be a laser cutter or a laser engraver. The reason it's extremely fast to process and extremely fast to design for is that you have very limited degree of freedom, typically no more than just a 2D pattern. So as long as you're able to do the 2D design pattern, you can blast one out in no time. And lasers can do plastics and metals, the water jet can do more, glass, ceramics, exotics like carbon fibers and other things. So the thickest we've ever done is a 6-inch slab of titanium on the water jet in the center. So sheet processing, first in your toolbox. Very fast, but very limited. Next we have something called subtractive machining. And if you have a look at the video, you can clearly see it working. Effectively, subtractive machining means it's like sculpting. You start with a block and you take pieces away. So it's broken down into two types. Milling, where the block is held fixed and the tool spins against the block. And you can see here a end mill pushing into the side of a piece of aluminum and throwing the chips out the back. Typically, the machine moves in what I would call 3-axis, which is the ones you're familiar with in the CAD tool, X, Y, and up and down, which is Z. It is possible to twist the stock around and do lots of other cool things with it in multi-axis machines, and we have multi-axis support. The design requirements go up for subtractive machining. You've got more things you can do, therefore more things that you have to design for. Mostly this technique we have works with plastics, metals, woods, etc. Then we have the other main class of machining, which is turning. This is where the tool is not moving, or rather is not spinning, but the actual block that we're working on, in this case a rod, is spinning. And it is fantastically good for round parts and anything with a kind of spherical or oval geometry. As you can see, it naturally makes perfect round shapes. The machine that typically does turning is called a lathe. And again, XYZ, multi-axis is possible. And again, plastics, metals, woods, and so on are all possible. So milling for when you want details inside a block, like the Titan 1M. Part, and turning for when you want rods shapes, majority of rod shapes. Then last we come to additive machining, though definitely not least. You probably have seen 3D printers, I'm sure you're familiar with them. The center has one that can do plastics, we can do continuous carbon fiber reinforced plastics, and we can do metal 3D prints. So we have quite a variety available, but basically there is no stock block. The material is specifically added by the printer. Is, X, Y, and Z is possible. Multi-materials are also possible. So again, it's quite a rich technique. This one's the new kid on the block, and it's certainly the new kid on the block in a cheap way. There's a lot of design choices you have to make, but additive is a really powerful tool in the armory. So now we've discussed our main materials and so on, and our main processing steps. And again, very quickly, sheet processing, blindingly fast. Then we got the two types of subtractive, milling and turning. And then finally we have the additive, which is 3D printing of some kind. Effectively, you are going to be the designer. Unlike the Titan 1M, where you're given the information, now you have to decide for yourself, okay, what am I designing? So be thinking about the materials and processes when you actually make your model. So if you know it has to be of metal, you're probably looking at subtractive machining or 3D printing. In all cases, if you can think about what you're doing, if you can get away with sheet processing, you're going to get done fast and you're going to be happy with the result. Next up on the list of processes I would recommend is additive, because the 3D printer runs while you are getting on with your work and activity without the 3D printer. You don't have to babysit the 3D printer and be present for most of it. So additive is a good use of your time. And if you are going to do subtractive machining, I highly recommend printing it via an additive print to check size, fitting, and other things. And lastly, we have the subtractive printing, which is able to make stuff out of the much more harder materials. So those are the order in which I would consider all processes normally for any part that you want to work on. And the main question you usually need to be asking yourself all the time is, how simple can I make my part? Now, in some of the exercises, you'll see a lot of curved parts, and you may think, oh, a curve is really complicated. Well, with a computer-driven machine, actually a curve can be considered simple because it gives the machine a much smoother operation. We'll get into a lot of that as we go through bits of the class to kind of tune up your knowledge. But fundamentally, think sheet processing, additive, and then subtractive. Think how many axes can I actually design for? How many can I achieve? For example, subtractive milling, the standard 3-axis milling is simpler, but it really only... if all your holes are vertical and all your features are vertical, then 3-axis CNC milling is fantastic. If they're not, then you're going to either have to do multi-axis, or you're going to have to design it so you can take your part out, rotate it, put it back in the vise, and attack the other side. So you can see that the choices you make, the features you put in your model, can rapidly make your life more difficult. So the simpler you can make it, the happier you're going to be. Now, CAD for manufacturing. Let's contrast the Titan 1M with something that you're designing. Now, the Titan 1M that you're supposed to have done already, as of the last lecture, the key thing is the Titan 1M was already designed and you got a diagram sheet with all the specifications provided to you. So what you were doing there was an exercise in CADing up an existed known good design. I would contrast that. All of your designs are going to require some back and forth, some iteration, some tuning, some tweaking for your success. The Titan 1M design that we saw had very low value on flexibility or reuse. Basically, they copied the print perfectly, which is what the exercise was about. But basically, if you wanted to change the size of that, you'd have to redo the entire thing pretty much and move everything to get it updated. So we're going to be taking you through parameterized CAD in the next section, which will go about how you make things a lot more flexible. You must understand, as a general comment, I find students have been taught over almost, 5 to 7 years of schooling, if not longer, that effectively you do work one time, you get a grade, and you never use that work again. So again, you put something in for a grade, it gets graded, and you never use it again. In the real world, that is completely wrong. You never get to give up on your old designs. Someone will always call you years later on something you did years ago, or you yourself will have to dig out something you did years ago. It's a completely different philosophy. So design your design and model your stuff with the idea that other people are going to want to change it, other people are going to want to tweak it, you are going to change it, you are going to tweak it. It's going to be read far more often than it's going to be written. That if you design simply, you can change the machine you use, the processes you use, tooling. These will all be things that be quick. Whereas if you do the kind of work that you saw on the Titan 1M, what you're going to end up with is something that works in only one situation, and that, you're in a new situation now, and you're going to have to spend all that time designing it again. So be very mindful of designing with the idea that you will have to change it in the future, because it will be wrong. Okay? Which is very different from I have a print with perfect information and everything is correct the whole time. So, after that, let us move on to actually looking at the CAD software and parameterized and working with CAD.